These are my four vectors. That's the first one. They very, I copied a few vectors from the four, but some of them are slightly different. Again, it's four tuples, quadruples, I should say. x2, x1, x1, x2, x3, and x4. These are my vectors now. Again, if I raise the same issue, whether I can make the linear combination of these vectors work into zero even though not every coefficient is zero. So you see, I just take the linear combination of these vectors and I substitute my vectors right on the spot. I equate this to zero and I raise the question whether I can find unknowns lambda such that they will work for this relation, but not necessarily everyone is zero. This is about systems of linear equations again. Here's the augmented matrix of my system. I just copied all of the vectors as columns in here. First column, second column, third, and fourth. It's a very streamlined process when you do it a few times. I bring it to the row echelon form. Again, I hide the steps which do so. You can recover those steps in your own time. Pay attention to the metrics this time. This time, not every column will be, that was the intent of this example. You see, my last column is no longer the leading column, which suggests there will be multiple solutions. There will be parametrized solutions. Here they are. You can back substitute. You parameterize the unknown for the non-leading column. That's my parametrization. And then you solve for the rest of the unknowns. This is a lambda 3. Lambda 2, lambda 3 from the third row, I should say. Lambda 2 at the second row, back substitution. Turns out to be t again. And lambda 1 from the first row. That's the solution for lambda 1. We have this multiple parameterized solution. I don't actually need when you do this in the context of linear dependence or independence, all you have to find is just one set of lambdas which work like this and such that they are not necessarily zero, all of them. So you don't have to actually parameterize. Often when I do this in a time stress environment, I don't even parameterize. I just choose lambda 1 of some non-zero number, say 1, and I solve for the rest in terms of that 1. Like in this case, if I choose here 1 rather than t, my lambdas will be these coefficients. Minus 1, 1, minus 1, 1. These coefficients, they mean, I don't have anything typed like this. These coefficients, they mean that if I take negative 1 times first vector plus 1 times second vector plus negative 1 times third vector and plus 1 times the fourth vector, this will be 0. This is that linear combination we were hoping for, and we found that in here by replacing t with 1. So if miraculously you have such a powerful guessing machine, I think you can produce these coefficients on the spot without doing all of this. And the question was, confirm that these vectors are linearly dependent. That's all you have to do. I mean, if I know these coefficients already, I don't have to redo all of this. All I have to do, I just have to tell that if I use these coefficients and just verify and just compute the left-hand side with these coefficients, it will be 0.